Again, it's a red stick.
What is going on, guys? Welcome back to the Algorithms and Data Structures tutorial series. In today's video, we're going to take a look at the most important runtime complexities that you need to know about. We're going to compare them mathematically, visually, and asymptotically, and we're going to also talk a little bit about how they come into existence. So let us get right into it. So let's start with the most desirable one, which is the constant runtime. And a constant runtime is represented visually by a horizontal line because no matter how big the problem instance gets, I'm always going to have the same amount of steps. So for example, let's say we have a linked list. Even if you're not really familiar with a linked list, it essentially means that we have elements in a list-like structure, but to get to element number 5, we talked about this already, we need to iterate through all the elements before that. Now, it doesn't matter if the list has 1,000 elements or 5,000 elements or a quadrillion elements or just 5 elements. To access the element at position number 5 takes 5 steps. Next, 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 and I'm there. So this would be a constant runtime complexity. It would not be 1 as we see it here. It would be 5. So let me change that. Essentially means 5. So a constant runtime complexity is not growing. It's always going to be the same, and this number can be extremely high, but it's still going to be the most desirable thing. Now, in real life, you're not going to encounter a constant runtime of, I don't know, a quadrillion, so it doesn't matter. But this is usually what we hope for. This is the best case scenario. You cannot get better unless a problem is already solved, then you need 0 steps. But essentially, this is the best runtime complexity that you can have. It's essentially not growing. The growth is 0. So the next best thing that you can hope for if you're not having constant runtime complexity, but you still want to have a very small runtime complexity, so a very, very slow growth, what you want to hope for is the logarithmic runtime complexity. And a logarithmic runtime complexity looks like that. It's the logarithmic function. And this essentially means that it's growing, but it's growing very, very slowly. It essentially means no matter how high I get, I'm going to have a very, very slow growth. Now this in this case is the logarithm of base 10, so it's growing even slower than the logarithm of base 2, for example, or the natural logarithm. But it essentially is a very, very slowly growing function. So it's not fast, it's not constant, it's still growing, but it's very, very slowly growing very slowly. So it's a very desirable runtime complexity. And you get it whenever you're, for example, dividing a list by 2. In divide and conquer algorithms, you always have at least some part of it is logarithmic because you have a full list of, I don't know, 20 values. And what you do is you then say, okay, take half of it and discard the other half. So essentially you're halving the problem size. You have, instead of 20, you now have 10. And then you have it again and you have 5 and so on. And this is essentially, in a way, logarithm base 2. So this is where this logarithmic runtime complexity comes from, and this is a very, very desirable one. If a problem is solvable in logarithmic time, and there are not a lot of problems that are solvable in logarithmic time, but if a problem is solvable in logarithmic time, it's a very, very easy to solve problem because it's very efficient. Now what you can also see here is the concept that we already talked about, that constants do not matter. So in this case, I choose 5 as a constant, and 5 is more than just, 1 times something. But logarithm is growing, and because of that, eventually it's going to always intersect with this constant line. Logarithm 10 is growing very slowly, so if I pick a huge number for the constant function here, so if I pick 5,000 or something, we're probably not going to be able to visualize it because I would have to go to extremely high numbers, to 10 to the power of 5,000, in fact, to show you that this function intersects with the constant function, but it will intersect eventually no matter how high the value is. But we can go to 10, for example, and you can see, yes, the logarithm is growing very slowly, but eventually in a very high numbers, it's going to intersect. And I hope I'm able to visualize this here, not going out of range. Eventually it's going to pass the function and to dominate it. So you can say it's definitely limited by the logarithm. So the logarithmic function, obviously, since it's growing, is less efficient than a constant time. Now, the next thing that you want to hope for if you're not having a logarithmic function, if you don't have logarithmic growth and you don't have constant growth, what you want to have is linear growth. And linear growth is essentially just Okay, now the scale is a little bit too fucked up here. Linear growth is essentially the same amount of additional steps for each new element added to the problem. So for example, if I'm working with lists, one new element means X amount of steps. Two new elements mean 2X amount of steps. X can be whatever. So in this case, I just have the function, let me just get rid of the constant function here. In this case, I have the function y equals x, which is essentially just a normal linear function. But any function that looks like that, like a straight line, is essentially a linear function. So I can go ahead and multiply this by 3, for example. It's going to be steeper. I can also go ahead and multiply this by a smaller number. So for example, I can go ahead and choose 0.2, for example, and it's going to be a more flat line here, less steeper line. But you can see it's still growing, and it's growing at a constant rate. So it's not slowing down the growth the way that a logarithmic function does it. It's actually having the same growth all the time. So of course, if I go ahead and pick a constant function here and give it a value like 9,000, it might be a large value, but eventually, sooner or later, if we scale that down, where are we here? 9,000, sooner or later, even with that 0.2x function, it's going to reach that state. As you can see, it crosses this function. So obviously, linear time is definitely worse than constant time. So whenever a function dominates another one, it's worse because we're hoping for small values, not for large values. So we want to have slowly growing functions. So this is linear time, essentially the same amount of steps needed. So in some algorithms, when you add one more thing, you need to do one more step or two more steps, whatever it is, a constant amount of steps for every problem. Whereas in other algorithms, you're going to have to add for each new thing. For example, if you're going to, let me give you a linear example. We already talked about it, is when you are looking for the maximum value of a list. When you're looking for the maximum value of a list, you need to go through all the elements in the list, and then you just pick the largest one. When you have one additional element, you just need to do one additional step. The same thing is if you have a list of numbers and you want to do 3 steps on all these numbers. So you go ahead and take each number, square it, divide it by 2, and then, I don't know, add 50 to it for whatever reason. These are 3 steps. And if you add one new number, you have 3 more steps. It's still linear because you have the same amount of steps. It's not depending on how many values are already in there. You have one n and that's it. Now, the next thing that we're going to look at is a combination of these two, of logarithmic time and linear time. And this is the so-called pseudolinear time, oftentimes referred to as pseudolinear time, because as you can see, it almost looks like a straight line because it's composed of the linear time and the logarithmic time. Its formula is n log n, which essentially means linear times logarithmic, and linear has a constant growth. It's just a straight line, and logarithm is essentially, when you look at it, it's growing, yes, but it's growing very slowly. It's almost not growing. It's flattening out. Over time, it's even growing slower. So the higher you get with pseudolinear time, the more it actually looks like linear. So the more you progress, the more it looks like a straight line, even though it is not. It's a curve because you have log n as a factor, and log n is depending on n, so it's growing with the input size. So this happens oftentimes when you're working with divide and conquer algorithms. When we're working with merge sort, for example, quick sort, whenever we're splitting lists, whenever we're splitting problems and dividing them and conquering them, we're encountering this n log n time. For example, merge sort is an algorithm, sorting algorithm that we're going to talk about, that has a runtime complexity of n log n. Worst case, best case, I think, as well. And that's essentially it. You can now compare this to linear. Let's just choose a different factor here. Let's say this is 4n. So the linear function, you can see, okay, it's steeper, and you could say, okay, if that is linear, it should never pass the green one. But we can go ahead, scale down the coordinate system. You'll see it's not linear, it's just pseudolinear, because eventually when we get to the bigger numbers here, I will definitely find a moment where this purple line crosses or intersects with the green line. And from this point on, as you can see, the purple line is now dominating the green line, which means that it's less efficient. However, practically speaking, it's almost the same. It's definitely growing faster than a linear time, obviously, but it's still a very good runtime complexity. So if you can solve a problem in n log n time, it's still very efficient. Next up is the so-called quadratic time. And now we get into some runtime complexity that is not as efficient anymore, because now we have pretty fast growth. Compare this to something like for x, rapidly outpacing it, rapidly getting more inefficient, less efficient than it. Also n log n, even if I add something like, I don't know, 50 to it, 50 times n log n, the turquoise function here is going to outpace this function very quickly because it grows very quickly. Even if I pick 50, it doesn't matter because n squared is growing way faster. So we don't even have to go to extremely high numbers here. You can see it happens at 100 already. It's outperforming, or not outperforming, actually outgrowing it, which is bad, so not outperforming. And n squared is essentially a runtime complexity that you're going to encounter very often. It's whenever you have to consider all the other elements that are already in the list and perform each operation on each element. So I hope this is not too confusing, but we talked about this already. If I have a list of numbers and the job of the algorithm is to take each number and multiply it by itself and all the other elements, then go to the next element and do the same thing with all the other elements and itself. When I add a new element, it's not just that I have to do this for the element, I have to multiply this element with all the other elements and itself, which has a dependence to the amount of elements already in that list, but I also have to go back to the other elements and multiply the other elements by this new element, so I have something like n squared. So compared to something like linear time, pseudo-linear time, logarithmic time, it's not desirable, not efficient. A lot of sorting algorithms that are less efficient are considered to have a runtime complexity of n squared. For example, bubble sort has a worst case runtime complexity of n squared. I'm not sure if it has an average runtime complexity of n squared. I think it has. But n squared is essentially not good. But for some problem again, for some problems again, it is, because if you can solve a problem like sorting in n log n, of course, n squared is very, very unattractive. But there are a lot of problems out there, and if we were able to solve them, some of them in n squared time, in big O of n squared, so to say, that would be a revolution. So n squared, even though it's very slow and inefficient compared to log n or to linear time or pseudo-linear time, whatever it is, it's still very, very efficient compared to exponential time, because n squared might not be as efficient, but it's solvable. It is doable. We can work with n squared. It may take longer, it may take long, but it's not necessarily something that's impossible to solve. We can definitely work with n squared. Same goes for anything that is n to the power of a constant, so n to the power 3, n to the power 4, n to the power 5. Yes, n to the power of 3 is growing faster than n to the power of 2, but still, as long as it's of the format n to the power of some constant, it is still polynomial time and it's solvable. We can work with it, and we consider these, I don't know if possible is the right word, but manageable problems. We can work with them. And now we're getting to the functions, to the runtime complexities that we consider not manageable. These are runtime complexities that you really want to avoid. You don't want to have them. And the first one is exponential growth. Exponential growth means you have a constant to the power of n. So up until now we had n to the power of a constant. Now we have a constant to the power of n. And this constant can be 2, this constant can be 4, whatever it is. It essentially means that n is the exponent. So compare this with x to the power 3. This red function here is 2 to the power of n. And this yellow function is n to the power of 3. Even though it might seem as if this function is growing faster, 2 to the power of n is definitely going to pass this. So let's just scale this down a little bit, and you can see it's passing it quite quickly already at x equals or n equals 10. You can see that the red function is already outgrowing it by a substantial amount and very fast. Exponential growth is really dangerous. This is what you really want to avoid in any way. It's extremely, extremely fast growth. And even if you don't pick 2, as long as the number is larger than 1, obviously, because 1 to the power of, I don't know, 1 million is still 1. But as long as you have something like 1.1 to the power of x, it is still going to outperform these other polynomial function, even if it takes a little bit longer, but we don't even have to wait too long. It's exponential growth, so the growth is growing. The growth itself is growing really fast. And as you can see in like 150, even though I'm dealing with 1.1 to the power of x and x to the power of 3, you can see it's outperforming it easily. And you can do the same thing with, I can also say, I don't know, 50 times x to the power of 3, and I still have 1.1 to the power of x. It doesn't matter. Again, outperformed. And we're at very small numbers here. So I can go ahead and do this with 500. I can play around with this. You're going to see exponential growth. You don't want to fuck with it. It is really not something you want to work with. Exponential growth is outperforming everything. I can also go ahead and say x to the power of 5. Who cares? It's going to take longer, but sooner or later, okay, I cannot, oh yeah, I can. I can even scale it down at around 360, 370. 1.1 to the power of x is outperforming, not outperforming, dominating 500 x to the power of 5. So you can see polynomial time is nothing compared to exponential time. This is really something you want to avoid. And how does this come into existence? For example, if you have recursion sometimes. For example, if you want to implement the Fibonacci sequence recursively, what you can do is you can go ahead and write a recursive algorithm of start with two fixed values, like the first one is 0, the second one is 1. And then what you do is you do two recursive calls, and you essentially say, okay, give me the last number n minus 1 and the second last number, which is n minus 2. And essentially what you're doing is you're having recursive calls, and for each two recursive calls, and for each of those you have two recursive calls again, and for each of those two recursive calls again. If you don't using dynamic programming or anything like memorization or something, you're running into exponential time. And this here is 1.1 to the power of x. If I increase this to like 5, you have no chance. Like, this is extremely fast growth. And exponential growth is definitely something you want to avoid. Just keep that in mind. But it gets even worse, because exponential growth is not the worst thing that you can have. You can also have factorial growth. And factorial growth, for those of you who don't know what factorial is essentially, if you have n factorial, this means n times n minus 1 times n minus 2 and so on until you get to 1. For example, if n is 50, it's 50 times 49 times 48 times 47 until you get down to 1. And this is I'm not going to say outperforming again, it's dominating, it's limiting, it's essentially worse than exponential growth. So as you can see, even if I pick something like, I don't know, let's go with 9 to the power of x, even though that's a very fast growing exponential function, we're going to see that this factorial function here is definitely going to intersect with that red function. I hope we have enough scale here to show that, but I think it should be possible. Otherwise we have to lower the exponential constant a little bit. We have to lower it. Let's go with not 9 to the power of x, but 7 to the power of x. 7 to the power of x. And now you can see it happened somewhere down here. The green function passed the red function, because factorial growth is faster than exponential growth, because essentially you're multiplying n times n minus 1, which gets you gets you into very high numbers quite quickly. So this is even worse, but fortunately it's not happening too often. It happens when you try to find out all the possible permutations of elements, for example, but factorial time is not something that usually will happen to you in a normal algorithm. But even if you think factorial is the worst thing, there's one thing that's even worse, but it's just something I want to show to you. It's not really something that happens quite often, and it's n to the power of n. So it's exponential growth, but not only the exponent is growing, but even the constant, so to say, the variable, the base is growing. So this is the pink function here, x to the power of x, and this is an extremely rapid growth. So you can see it's going to dominate these functions quite quickly and forever. So this is even worse. So if you have x to the, or n to the power of n, it's worse than factorial, but I cannot really think of an example where this is going to happen. So this is just to show you that it's even worse than n factorial. But the worst thing that you can realistically encounter in a normal algorithm is going to be n factorial, or most of the time it's going to be exponential. And exponential is something that we cannot really manage. So if something is only solvable in exponential time, it's very, very hard for us. And if we don't have any polynomial solutions, we cannot really say that we have a good solution to the problem. So that's it for today's video. I hope you enjoyed and I hope you learned something. If so, let me know by hitting the like button, leaving some comments in the comment section down below, and subscribing to this channel if you want to see more future videos for free. Other than that, thank you very much for watching. See you in the next video, and bye.